Hello everyone, welcome to Study Tech, the home for electrical engineering students. Why open circuit test is performed on LV side and short circuit test on HV side? This is a very much conceptual question, as theoretically as practically, because we have done all these experiments, the open circuit test, short circuit test in our laboratories. Okay, so before starting discussion, let me tell you one more thing, that is this question, as because this question needs very much conceptual understanding, so I recommend you to watch this video from starting to the end so that you can get the concept step by step, and at the end it will be clear, I hope so. So let us go to the next slide. Okay, look, first I am going to discuss why we perform this experiment. That is the objective of this experiment. Okay, the first objective is to find out equivalent circuit parameters. This is our first objective. Second objective is we have to find out the voltage regulation of the transformer. Okay, if you do not know what is voltage regulation, please watch our videos. Stay tuned with Study Tech, many videos will be coming. Next thing is we will calculate efficiency of the transformer. Okay, so these are our objectives, and to meet all these objectives we need to perform two tests. One is your open circuit test, another is a short circuit test. Two tests are performed. One is open circuit test and another is called short circuit test. Sometimes it is called the OC test, sometimes it is called the SC test. Well, so let us go to the open circuit test first. Well, so the open circuit test, to get the open circuit test, look, this is the circuit. This is the circuit. This is a equivalent circuit, or you can say the connection actually, and this is the phasor diagram. So look what is happening here. We will keep this terminal open. Sorry, OPEN, right? We will keep this terminal open. Now, why we have chosen high voltage side to keep open? That may be a question. Well, before that, what we will get from this open circuit test? From this open circuit test, we will calculate the iron loss or the core loss, because we know that the transformer draws in the secondary. When you connect some load, transformer draws two currents. One is a IO, one is I1 equal to IO plus I2 dash, and this is due to loading in the transformer. So if I do not load the transformer will only draw the no load current I0. And remember at this point one thing, that is this I0 is very small. I0 is around your 2 to 6% of this full load I1. 2 to 6% of I1. So can you assume how much less it is? Okay, so what we will do, we will keep this side open, but we have chosen to connect the meters, we have chosen low voltage side. The reason is, number one, that is for the low voltage side, the voltmeter required, that will be of less rating. Assume this is a very the low voltage side is of low voltage and high voltage side is of very high voltage rating, then you may not get the rating of the voltmeter which is capable of measuring this voltage. So but in that case, if we use the low voltage side, then it will be good, because we can get the meters of low rating, or in the other way you can say the low rating meters, or the low range meters can be used for measuring this voltage during the open circuit test. That's why we choose the low voltage side to connect this voltmeter and also the other meters. Now there is another, this will be, I hope, ammeter. I have taken this diagram from the book, Bhimra's book. If you, for the reference, you can go to the Bhimra's book. Okay, so the ammeter has been connected in the low voltage side. As you know, that is a high voltage side means low current side. High voltage means low current side and low voltage side means high current side. Right. Now you may argue with me, that is, if this is this side, sir, this side is of high current side. So why do you have connected this ammeter here? So you need the ammeter of higher rating. Okay, but the answer is yes, the point is true, but the thing is that the transformer, that is the auto transformer, is connected here. Okay, we will start from here. Gradually we will apply the voltage, the rated voltage here. Okay, once we apply the rated voltage here, the transformer is not drawing any current, sorry, the I2 is 0, meaning I2 dash is 0, so transformer is drawing only I1, which is nothing but IO. Okay, so I1, the rated current I1 may be very high, but right now the transformer is drawing only the no load current, which is 2 to 6% of the total current. If it is your, let's say, 10 ampere, this will be only 2 ampere. Okay, so even if this side is high current side, but a low range ammeter is capable for measuring the 2 to 6% of that high current. Okay, is it clear? So voltmeter, ammeter, that's why we choose the low voltage side for the connection of the meters. Now the wattmeter will read you the power loss. Okay, what the power loss is happening here? The power loss that is happening here is the transformer, as because the load current is 0 because of the open circuit, the transformer is drawing only the no load current I0. We can say in the equivalent circuit, if you have not studied the equivalent circuit of the transformer, please watch our videos how to draw transformer phasor diagram. There I explained the transformer equivalent circuit, the whole equivalent circuit. This part you can, if you remember this thing, look, this is a applied voltage. Okay, so this applied voltage IE, here they have used IE, the IE or I0, whatever it is, IE or I0, same thing. It is flowing through this one. It is for core loss and that is for the magnetizing component. And here the I2 would flow, but that is 0 due to the fact that we have kept this high voltage side open. So basically the transformer is drawing the input current that is used for the two purpose. One is to satisfy the core loss, and this is for the flux. So the current is here used for two purpose during this test. One is for satisfying the core loss, because the core loss will happen in the transformer, and another is to set up the flux. Now the thing is that, remember one thing, the core loss depends on the voltage. You have to apply, if you want to find out the rated iron loss or the rated core loss, what you have to do, you have to apply the rated voltage at the low voltage side. Let us assume this is 100 volt, this is 200 volt. So gradually you have to, the first and foremost criteria is you have to, by using this what to say, this on a variac, using this variac, you have to apply this 100 volt, then you have to read the reading of the wattmeter, and that time reading of the wattmeter will give you the core loss. Okay, the ammeter will read you I0 and this will read you the rated voltage. Okay, and this is iron loss. Now for the calculation part, I will refer to the phasor diagram. Let us go to the next page. So is it clear why we chose we have chosen the low voltage side for connecting the meters? Well, let us go to the calculation. Well, for the calculation, look, this IE is there, no I2 dash. There would have been I2 dash, and then you would get, in a phasor diagram, you would get this one is your IE, but these parts are not there, so basically IE is there. So now we can calculate one thing, because we have the reading W, we have the reading I, we have the reading V. Three readings are there. Okay, so for this, from this three reading, we can say that for the calculation part, the cos theta, this angle, okay, this angle cos theta, cos of theta 0 can be written as PC, the wattmeter reading PC, okay, the IO and the V1. Well, what happened? Let me change it. Well, now it's okay. So what is happening? This the cos theta will be this V1 IO. Well, because the wattmeter reading PC is nothing but the VI cos phi, right? The power loss for the mainly the core loss, because I square R loss will not happen here because I2 dash is 0. Okay, so the shunt this in this path current is not, almost negligible current is flowing, you can say, and that's why the power loss due to this I square R in the series parameters is not happening here, we can assume, or we can neglect it. So PC can be written as V1 I0 cos theta 0. So from here you can calculate cos theta 0, right? So once you have calculated this cos component, now we can say that is a IC part, the core loss component IC will definitely be I whatever the I0 is, IE is the same thing. Okay, let us, they have used IE, let's see, there's IE cos theta 0 and IM will be IE sin theta 0. So once you have calculated cos theta 0, from here you can calculate sin theta 0, right? So from there you can calculate IC and IM. Once you have calculated the IC and IM, now can I say this IC will definitely be, sorry, RC, right? The core loss resistance will be this voltage divided by this current, and IC is known to you, and V1 is known to you. V1 by IC, and XM can be written as V1 by IM, right? So using this we can calculate the RC and XM. Okay, is it clear? So what we did, we know that the power loss equal to V1 I0 cos theta 0. From here we have calculated cos theta 0. From there we calculated sin theta 0. From there, from the phasor diagram, now we know that theta 0 is known to you and IE is known to you. You can calculate this IC, which is nothing but the cos component of IE, and IM, which is nothing but the sin component of this IE. And thereon, from this phase of the equivalent circuit, you can calculate RC, you can calculate XM. Well, remember one thing, from OC test we get the the shunt branch parameters. Okay, so this is a calculation part. Let us go to the next step, that is a short circuit test. Same thing we will do, only the difference is we will short circuit the LV side. We will short circuit this LV side, okay, and we will connect the meters in HV side, and the process will remain same. We will take a variac, and starting from 0 we will gradually increase it, and the condition is rated current to flow. We have to make such arrangement such that the rated current flows here. Okay, so how that is possible? Look what I have made. We have made this is, look, this is E2 here. If we would connect some impedance or the load, there would have been V2, but V2 is here 0. So what we can say, I2 is only E2 by Z2, and previously it would be minus V2, but V2 is 0 here. So we can say the what I'm trying to say is that to circulate, think about this side, LV side. Okay, think about this LV side. What the transformer is doing, the transformer is circulating this current against its own winding resistance and the leakage reactance, and no other load resistance is here. So it has to overcome this drop only, this voltage drop only, okay, to circulate the load current. Now we can say, if you apply, this is a high voltage side, 200 volt, this is a low voltage side 100 volt, but 100 volt during the short circuit 100 volt is not required to force the secondary rated current. Now look, if there is a 100 volt and V2 was, let's say, 80 volt, then the difference will be 20 by this impedance Z2, then the rated current would flow. Now what is happening? Now this is increasing. Okay, so I mean, what I'm trying to say, now this is short circuit, no 80 volt is developed here, there is only 100 volt, so 100 by Z2 will be much more voltage, right, isn't it? Now then what will say, 20 volt is enough to circulate the rated current. That's the thing I'm trying to say. You start from here and gradually increase the variac to 20 volt. If you put some meter here, put some meter here, ammeter here, you will see at very less voltage the rated current is flowing. The reason is very simple, that is there is no opposition of the load resistance, only it has its own winding resistance and the reactance. It has to overcome that part only, so it can overcome that own winding resistance and impedance reactance drop. Then small voltage is quite enough to circulate the rated current here. That the idea is, if you get this concept, I mean, I'm telling you, if you did not get the concept, again go to the back and listen what I'm saying, that small voltage is enough to circulate the rated current. If you get this concept, remaining part is very easy. Now we can say, let us say that in a small voltage, the rated current is flowing, and we can assume the rated current is flowing here also. Once rated current is flowing here, we will assume the rated current is flowing here. Now, small voltage has been applied. Now look, the iron loss depends on voltage, right? So as because the voltage has been applied very less, okay, 2 to 6% of the full load voltage, what will happen? This iron loss will be negligible here because the voltage has been applied small. Now think about the equivalent circuit. This is the equivalent circuit during short circuit test, and this portion will be cut out. This portion will be cut out because this current will be very small. Okay, so as if this is not there. Now the current is basically due to the load, and the current is I2, and here I2 dash, and the same thing. Okay, now we can say the current during the short circuit test, this shunt branch parameter is not there, but the series branch parameters are there. So this will be the equivalent circuit during the short circuit test. Another question is, why we have connected the meters here in the HV side? Number one, as you have seen that the rated current will flow. First of all, high voltage side means low current side, right? So the low current side means we can take a low range ammeter, that is enough. The concept is clear. The same argument I am applying here. The high voltage means low current, so the ammeter range, small range ammeter is enough to read this current. Number one. Number two, the voltmeter. Now you will say that the voltmeter, why you have chosen the high voltage side? You have to connect a high range voltmeter, but the answer is again no. You have seen a bit ago, that is to circulate the rated current in the secondary as well as in the primary side, you don't require the 200 volt. If it is 200 volt, you will need 2 to 6%. Well, it will read just a small fraction of the high voltage side. So you can use a low range voltmeter, that is quite enough to read 2 to 6% of this high voltage. Okay, so that's why we can safely use the low voltage, low rating voltmeter. And wattmeter, what about the wattmeter? The wattmeter will read the transformer loss in the I square R branch. Okay, so that the thing is, I hope you get the concept. The same argument we did for the open circuit test, and the same argument we are doing for the short circuit test. Now we need to do some calculation. Well, for the calculation, we can say in this circuit Z, look this circuit. Okay, so the total impedance will be, you have the reading Z EH in high voltage side, the reading will be V short circuit by I short circuit. You have the wattmeter reading, you have the short circuit voltage reading, you have connected the three readings here basically. the VSC, ISC, right? So VSC and ISC, short circuit test. Once you calculate V by I, if you do the V by I, you will get the Z, right? And wattmeter is reading you I square R, PSC. As you know, in the resistance part, here and here, there will be the I square R loss and no current is flowing here, so I square R. So we can say ISC square into REH. What I'm trying to say, ZEH, REH, if you are getting confused, the impedance referred to high voltage side, impedance referred to the high voltage side. Like you do the resistance and the reactance terms, they are referred to primary side, referred to secondary side, that thing. We are using H and H as to uh, specify that they are referred to the high voltage side. That's it. Well, so from here, if you know this reading is known to you, this reading is known to you, you can calculate how much REH is. Now here, this is known to you, this is known to you. So R is known, Z is known. So XEH can be calculated as the Z, sorry, so that is equal to ZEH square minus REH square. You will get to know the value of XEH. Now look, now you have all the parameters. Let us go to the transformer. This is though you have not segregated R1, R2, but we have calculated the referred resistance and referred reactances. Okay, so now from these two tests, open circuit test and short circuit test, we get to know the equivalent circuit parameters. Okay, equivalent circuit parameters. Then we get to know the PI, the iron loss. We get to know the full load copper loss. This PI will give you from the open circuit test, and I square R you will get from the short circuit test wattmeter readings. Now you have many datas in your hand. Equivalent circuit parameters is done. To calculate the voltage regulation, you know the formula. Okay, E2 minus V2 by V2. So you can apply that. There is a formula, epsilon R epsilon X. Okay, so apply on that formula, you will be getting that value, voltage regulation. Now you can calculate the efficiency. To calculate the efficiency, you know this output by input, and you can calculate is a V2 I2 cos phi 2 plus this thing plus the losses. Okay, we will discuss the voltage regulation and the efficiency in another video. Here I told you that is the data that are obtained from the open circuit test, short circuit test. We can calculate the equivalent circuit parameters. Okay, well, if you have any doubts, any queries regarding this video, you can put it in your comment box. If you have liked the video, please share among your friends. And many a times you will be facing this question in theory, or many a times in what to say, the interviews. Okay, they will ask you the question. They want to know actually which one is preferred as a metering side. If you just can't get the point, that is in open circuit test, you apply the rated voltage. Why apply the rated voltage? You want to get to know the full, I mean the iron loss. To find out the total iron loss, you need to apply the rated voltage, because the iron loss depends on the voltage. Number one. Number two, and there the I square R is negligibly small. You have to explain why I square R is negligibly small. And another question is why you prefer the low voltage side for connecting the meters in OC test. In second case, that is for the AC test, they will ask you why there is iron loss are negligible here, because we are not applying the full voltage. We are applying 2 to 6% of the full voltage. Okay, so the iron loss is negligible here. Iron loss is negligible. Now we are in short circuit test. Condition is you have to allow the rated current to flow. Okay, you have to allow the rated current to flow. Once you have allowed the rated current to flow, there will be I square R loss. Okay, then from the I square R loss you can calculate all these things. Well, why you use for the high voltage side for connecting the meters? The same argument can be done. Though it is a high voltage side, but you are not applying the full voltage. You are done a small fraction of it, 2 to 6%. So low voltage, low voltmeter, low range voltmeter is enough, and high voltage side means low current side. That's okay, fine. So that the answer is, well, I hope you have liked the video. Please share among your friends. subscribe our channel to get the more videos on different questions and different topics in basic in electrical engineering, different subjects. Thank you. Subscribe our channel and press the bell icon to get the notification for the further video uploads. Thank you very much.